This conference will now be recorded.
Okay, last class we have discussed that generating how we can construct the linear block code, and we have said that associated with a linear block code there exists a generator matrix, and we have seen the structure of that generator matrix. It is usually represented by the capital letter G. That initial part will be an identity matrix of the order k. We know what is meant by that k, nk for a linear block code. We know what is linearity, what is meant by block code. Then that nk represent the k is the number of message bits considered at a time in order to generate a code word. We are generating a code word corresponding to that k number of message bits, and we are generating a n bit length code word. And for that generator matrix, that G is an matrix of the order that initial part order of the matrix will be that k by n. Order of the generator matrix is k by n, and the initial part will be an identity matrix of the order k, and that remaining part we can consider it as a submatrix of that generator matrix, and it is termed as a p submatrix, p matrix of the linear block code. We say like that, p submatrix of the linear block code. It is once that p submatrix is given, we are able to write the generate or construct the complete code corresponding to that particular linear block code, a nk block code. Okay, that we have discussed in the last class, and we have done a problem. That is, a generator matrix is given for generating a 6-3 block code that we have seen in the last class. Okay, I think we can continue. Then similar to that generator matrix, there exists a parity check matrix, which is termed as parity check matrix, and it is represented by a capital letter H. That is, sometimes that H will be given in order to generate or construct a linear block code, a capital H, and it is termed as parity check matrix. That is, we can say for every block code, every linear block code, there is a q by n parity check matrix. The order of the check matrix, parity check matrix, that H matrix is q by n. We know that q is n minus k. Q is n minus k. Okay. Then the structure of the H matrix, the general form of the H matrix is, that is, this G and H are related. That is, we are generating or constructing that linear block code corresponding to a generator matrix given, or P submatrix given, or H matrix given. These all are related, and it is defined as, or we can say the general form of the H matrix is, general form of the H matrix is, initial part is initial part is the transpose of that P matrix. We know what is that P, that submatrix of that generator matrix. Then that initial part will be that transpose of the P matrix. Okay, I think there are no issues. You are audible and visible the screen. Okay, please someone respond. Can I?
Yes, sir.
I think no. Okay, I think no problem. Okay, the general form of the H matrix is that initial part is that transpose of that P submatrix. Then the second remaining part is an identity matrix of the order Q. Sorry, identity matrix of the order Q. We have that Q is equal to n minus k. That is, we have seen the generator matrix has the form IKP. This initial part is an identity matrix of the order k, and the second part we can treat it as a submatrix of that generator matrix. It is termed as p submatrix. Then here the H matrix, which is termed as parity check matrix. Its general form is p transpose, then an identity matrix of the order q. Altogether, the H matrix has the order q by n, q rows and n columns. And here the p transpose is the transpose of the p submatrix. That is one more add-ons takeaway from this session, that is that parity check matrix. There exists a parity check matrix associated with a linear block code. Okay, next you can take this problem. Uh, uh, and that part, some part will be solved now itself, and you can take this problem. The parity check matrix of a particular 7-4 linear block code is given by, please all of you please take this H matrix. H is 1 1 1 0 1 0 0. Therefore here in it is given the parity check matrix of a 7-4 linear block code. Therefore, n equal to 7, k equal to 4, k, n equal to 7, k equal to 4. Therefore, that q is equal to 7 minus 4, that is n minus k, that is 3. Therefore, that last part of this H matrix will be an identity matrix of the order 3, that is here 1 0 0 0 1 0 0 0 1, and that initial part given 1 1 1 0 1 1 0 1 1 0 1 1, that is a p transpose matrix. Actually it is the p transpose. We know what is that p in that generator matrix. Anyway, H matrix is given, that is a parity check matrix for the linear block code is given. uh, uh, Question is, we will have to write the generator matrix, then list all the code vectors. We are not wasting time for writing all the code vectors now. That is, here we know that is k equal to 4. Therefore there are 16 message combination possible, starting from that 0 0 0 0 0 0 0 1 etc up to 1 1 1 1. That is, here k equal to 4, therefore 16 message combination. And that second question is list all the code vectors, means we will have to write all the 16 code words. We'll have to write the 16 code word corresponding to that 16 messages. This the here we are discussing about the systematic linear block code. We know what is meant by that systematic block code. The initial part will be that message itself. Then here a q number of extra bits are added. Check bits are added for the purpose of error detection and correction. Okay, and here uh, q equal to 3, therefore 3 extra bits are added, and that message bit, 4 message bits plus 3 extra bits, that redundant bits, that check bits together forms the code word here. This corresponding to a code word corresponding to a message block of 4-bit length. We are generating a 7-bit code word. Okay, and third question is, what is the minimum distance between the code vectors? For that we will have to find the we know what is meant by minimum distance, that d minimum, it is the smallest value of the Hamming distance. Hamming distance is the that in how many bit position two valid code word differs. Then that minimum value of the all Hamming distance is the minimum distance, and we can easily determine the minimum distance of the code by taking the weight of the code. That weight of the code means number of ones in a code word. That is, here a 7-bit code word, then corresponding to each code word, we can that weight of each code word can be determined by taking the number of ones in that code word. Then avoiding without considering that all zero code word, the minimum weight of the code word, that is the minimum distance. In that way we can find the minimum distance of that code. Once that minimum distance d minimum is calculated, we can find the error detection and error correction capability of the code. Okay, uh, uh, you all of you please do the first part now. I have not included the solution in this slide. Anyway, you can write the generator matrix only now. The remaining parts you can do later. That is, the better way is write the in the question. It is asked the generator matrix. Therefore, we will have to write. And for listing all the code vectors, better way is initially write the equation for check bits. That is that C1, C2, C3. There are 3 check bits here. Therefore, we will have to write the equation for the check bits in terms of message bits. Here, take the message bits are M1, M2, M3, M4. Message bits, take it as M1, M2, M3, M4. Then write the equation for that message check bits in terms of that message bits. Okay, all of you please write the generator matrix. For that only we will have to do is initially write the p sub matrix. Okay, here we have H matrix is given, and we know the initial part here that 1110 1101, that is that 4 by 5 matrix that can be separated from the H matrix, that is the P transpose. Then from that we can write the P submatrix of this linear block code. Okay, take the transpose of this particular section, that 4 by 3 sorry 3 by 4 matrix, that initial part. Okay, initially all of you write the P submatrix. Follow this method. Can anyone say what is that P submatrix? Not to have a response, I need someone to please say what is that P submatrix of this linear block code. Here H matrix is given. From that, write say the P submatrix. It will be a 4 by 3 matrix. You can give one in the chat. What will be the first row of that P submatrix? Please say someone. Otherwise, I will ask some.
0 1 0 0 1 0 1 റൈറ്റ് സൈഡിലുള്ളതാണോ?
ഏതാണ്?
റൈറ്റ് പാർട്ട് അല്ലേ?
Left H matrix is of the form P transpose IQ.
Okay, okay.
P transpose IQ. Therefore, initial part that that can be separated a 3 by 4 matrix, that is P transpose. Okay. Then P is first row is 1 1 1, isn't it?
Okay,
P submatrix.
അതിലെടുത്തിട്ട്
Transpose എടുക്കുക, that is P matrix. That is here we can separate like this. This initial this part is P transpose. Okay, therefore take the transpose of this section. Therefore we can write that P is equal to 1 1 1, then 1 1 0, then 1 0 1 0 1 1. Here it is the P submat of that particular linear block code. A 3 by 4 sorry 4 by 3 matrix. I think you have got that. H matrix is given, therefore we are able to write the P submatrix. First question is generator matrix. We will have to write the generator matrix. Therefore we have that generator matrix have the order k by n, therefore a 4 by 7 matrix, 4 by 7 matrix, and for that initial part is an identity matrix of order k. Therefore, to left of this p submatrix, write an identity matrix of the order k, that is 4 here. Therefore, 1 0 0 0 0 1 0 0, like that. 0 0 1 0 0 0 0 1, that is an identity matrix of the order 4. Then that p submatrix here, rewrite this to the right of that identity matrix, write that p submatrix 1 1 1 1 1 0 1 0 1 0 1 1. Okay, this is the generator matrix. That is the first question, answer to the first question. Hope that you have got it. G is equal to. Okay, then next part you can do it later. I will say the method, that is last class we have done. That is, once that p matrix is obtained, it is better to write the expression for that check bits in terms of that message bits. Therefore, use the equation C is equal to m into p. C equal to m into p. Take that m as m1, m2, m3, m4. m1, m2, m3, m4 into that p submatrix. Write the p matrix here, p. For that gives equation for that 3 check bits, C1, C2 and C3. Equation for that check bits, it is equal to m1, m2, m3, m4 into that p. Therefore, we get equation for that check bits. That is, here we get C1 equal to m1 XOR m2 XOR m3. Okay, C1 equal to m1 XOR m2 XOR m3. Similarly, C2 equal to m1 XOR m2 XOR m4, C3 equal to m1 XOR m3 XOR m4. Therefore, by making use of that, taking all, considering all the message combinations starting from that 000 to 111, we can write the complete code word. There will be 16 code words. Once all the code words are written, you can calculate the weight of the code. From that, you can determine the minimum distance of the code. That is the third part, in the question. Then how many errors can be detected and corrected? That is that yes, errors can be corrected with if d minimum is greater than or equal to 1. Here in this particular problem, you will get 3, d minimum equal to 3, d minimum equal to 3. Therefore, by using this code, we can detect up to 2 errors and 1 error will be corrected, that with d minimum equal to 3. Okay, hope that you can do it later. Okay, okay, please someone say. I am moving to next portion. It is related to this itself, that is that decoding part. Can I? All of you please say yes. എല്ലാവരും ഒന്ന് എസ് എന്നൊന്ന് ടൈപ്പ് ചെയ്തേ ചാറ്റ് ബോക്സിൽ. എത്ര പേര് അവിടെ ഉണ്ട് നോക്കട്ടെ.
കേൾക്കാൻ കുഴപ്പമില്ല, ഫോളോ ഉണ്ട്.
ഓക്കെ. അല്ല, എന്നാൽ കുറച്ച് കൂടുതൽ എസ് ഒന്ന് വന്നോട്ടെ. ഓക്കെ. Okay, next is its decoding part, which is termed as the decoding part of the linear block code is termed as syndrome decoding. Syndrome decoding. This actually we are making use of one property of this linear block code for the error that is its decoding, that is that error detection and the correction. We have already seen that once that code is generated, by making use of that minimum distance value, we can say how much errors can be detected and corrected. Then here take the transmitted code vector is x. This here I am representing that capital X as the transmitted code, and the corresponding received vector I am representing as y, capital Y. Then we know if x equal to y, that is at the receiver end, that received sequence y equal to x, it means there is no transmission error. This x is taken as transmitted code word and y is the received code word or received code vector. Then that y equal to x means there is no transmission errors, that transmitted code is received here. Then if that x not equal to y, it means that some errors are created during the transmission. Okay. Then we have seen that with every nk linear block code there exists a parity check matrix, that is that h associated with every linear block code there exists a parity check matrix, that is denoted as h, and we have seen that its general form is p transpose iq, p transpose iq, and it is an matrix of the order q by n. Here this matrix symbol, no need of this. Anyway, h transpose h matrix there, which is termed as parity check matrix, and we can say the h transpose matrix. Here I am saying about the h transpose matrix, that is transpose of that parity check matrix. Here it has the form a p matrix and down to that p submatrix an identity matrix of the order q. It will be the structure, the general form of that h transpose matrix. Okay, if we take the transpose of the h matrix, it will be in form like this, that top part will be a p submatrix and the lower part will be an identity matrix of the order q. Okay, then okay, here h transpose matrix, we know what is h matrix, its general form p transpose iq. Then h transpose is p and an identity matrix of the order q. Then here that property used in syndrome decoding is, that is if we take the product, that matrix product of x and h transpose, is you can check it with the previous examples. That is we have one done an example in the last class and partially completed the problem. Today one more problem, that is generating or constructing that linear block code. Then you can check with it. If you take any valid code word, in the previous problem there are 16 code word we will obtain, multiply any of the code word with h transpose matrix, it will give a zero vector. That is that x, we have an 1 by n matrix. Okay, that is n, that is it will be a row vector, a single row vector or single row matrix which consists of n elements. That is that code word. N is the length of the code word. Therefore, X is a 1 by n vector. Multiply it with the H transpose matrix, which is an n by q matrix. Then we get a q number of zeros. That is, we can say a 1 by q matrix of all the elements 0. That is, if we multiply any of the valid code word with the H transpose matrix, we get a 0 vector. It is a property of linear block code. Linear block code ഏതെങ്കിലും ഒരു valid ആയിട്ടുള്ള code word എടുത്ത് അതിനെ H transpose matrix കൊണ്ട് multiply ചെയ്ത് കഴിഞ്ഞാൽ we get a 0 vector, complete zeros. That is, here strictly speaking, there will be q number of zeros in that vector. Anyway, X into H transpose is a 0 vector. Okay, if you take any of the any valid code word and multiply it with the H transpose matrix, we get a 0 vector. This can be used for decoding. That is, can you say some anyone can say how this property can be used for the decoding? X into H transpose is equal to a 0 vector. That is, here we can say X is the transmitted vector. Therefore, X is a valid code word. And if we take any of the valid code word and multiply it with the H transpose matrix, it will give a 0 vector. Then Y is the received vector. If Y into H transpose is non-zero, we can say some errors are present in Y. Okay, if Y equal to X, then Y into H transpose also 0. Okay, Y into H transpose also 0. If Y into H transpose, we get a non-zero vector. That is, that q 1 by q vector, in that there are some 1. Then we can say that Y into H transpose is a non-zero vector we have obtained. It means some errors are present. That is, the non-zero output of the product Y into H transpose is called the syndrome. This Y into H transpose, a non-zero output of the product Y into H transpose, is called the syndrome. I think you have got that what I have said. Here the property X into H transpose will be a 0 vector. Here X is a valid code word. If we take any of the valid code word of the linear block code and multiplying it with the H transpose matrix, it give a 0 vector. And Y, if we here the Y here is, here the Y is the received code word, and if you multiply Y into H transpose and it is getting 0, it means there is no error. Then if we get that product Y into H transpose is a non-zero vector, it means some errors are present in Y. That is, that X and Y not the same. Some errors are occurred during the transmission. And here that syndrome, the non-zero output of the product Y into H transpose is called the syndrome. That is S equal to Y into H transpose. Okay, here we are making use of this particular, it is detecting the error with the help of that syndrome and error vector. That is, the non-zero element of the S, the non-zero element of the S represent error in the output. Okay, the non-zero element of the S represent error in the output, and when all the elements of S are 0, two cases are possible. When all the elements of S are 0, the two cases are possible. That is, one is no error in the output. That is exactly the transmitted code word is we are receiving, and the other case is Y is some other valid vector other than X. That is, this means the transmission errors are undetectable. That is, we have, for example, in the last example, there are 16 code word, and one particular, that 15th code word is actually transmitted, and some error had occurred in some bit position, and it become another valid code word. Okay, then if we multiply the received code word with the H transpose, we get a zero vector. Therefore, there are two possibilities if S, that Y into H transpose equal to 0. One is no error in the output. Second is some other valid code vector other than X. This means that in that case, we are not able to detect the error. I hope that you have got what I have said. Can anyone say?
Yes, sir.
Okay. That is 2 points. One is initially that property X into H transpose equal to 0. That is actually we are making use of for the decoding, and that is detecting and correction at the receiver end. X equal to H into transpose equal to 0 means no error, and two cases when S equal to 0, no error in the output, and the other case is we have transmitted particular code word, and some errors are occurred, and it become another valid code word. In that case also, the product Y into H transpose will be 0. Okay,